universe. What a wonderful place to be in. It's interesting and it's also intriguing, which proves to be a fundamental reason to as to why we should study it. Cosmology is termed as the field that, simply put, studies the cosmos, and those who do so study the cosmos are known as cosmologists. And like any other field in science, to find an answer, you need to ask a very important question, an imperative question, without which we can't determine other factors of the field. And perhaps one of the most important questions to be asked in the field of cosmology is this: how old exactly is the universe? In 1929, Edwin Hubble combined his measurements of distances to spiral nebulae and the Doppler shift velocity measurements, which were derived by Westo-Slipher. He discovered that galaxies were receding at a rate proportional to their distance. He theorized this rate to be a constant, the Hubble constant. There have been two fundamental ways to calculate the Hubble constant, and they don't derive the same units. The thing is, though, that this issue has been obvious for a very long time, but the stark differences have only become more and more difficult to comprehend for us, since the uncertainties previously could be attributed to, say, technically unattainable factors, or the systematic uncertainties that we couldn't identify before. But this is literally the 21st century. We have become more advanced since then. We have made giant leaps in technology and data, and one would presume that these values for the Hubble constant would actually come closer and closer to becoming more equal. The issue is that didn't really happen. The first method we'll discuss is calculating the redshifts of pulsating Cepheid variable stars, discovered by Henrietta Leavitt, which are giant stars in the last phases of their lives, which we utilize as standard candles, a point to measure cosmic distances to calculate the value of the Hubble constant. Using an uncertainty component, the stellar parallax, humans have the ability to calculate remarkable distances. Adam Rees used the Type 1a supernovae as Cepheids, through which he was able to calculate distances up to 2 billion light years, earning him a Nobel Prize in Physics. The value derived for the Hubble constant using this methodology in 2019 was 73.5 plus minus 1.7 km per sec per megaparsec. The cosmic age here was derived to be approximately 12.7 billion years. Now that's value 1. Method 2 would be to use cosmic microwave background radiation. Here we track the baryon acoustic oscillations, the behavior of matter and light in the cooler, bluer regions. In the CMB chart is observed to evaluate further expansion taking place. The value derived for the Hubble constant here is 66.9 plus minus 0.6 km per sec per megaparsec. This was derived in 2018. Further, the cosmic age here was derived to be 13.799 plus minus 0.021 billion years. Now this is value 2. Comparing value 1 and comparing value 2 is obviously very, very concerning. You see, the error bars have only decreased in the last 50 years. Obviously, this is not soothing at all to see such massive inconsistencies in modern data in one of the most important questions in all of physics. This discrepancy in the Hubble constant shouldn't be happening at all. You see, ideally, both of them would derive the same values, but they don't. Luckily, we do have some popular theories on as to why this may be happening. Number 1 could be unknown systematic uncertainties such as biases or ethics. That's one way of looking at it. That's one outreach. In the second case, though, it may be due to, well, unknown physics itself. Maybe we're not looking at something in the proper way. Specifically in CMB's case, this could be due to the fact that maybe, just maybe, dark energy is just more inconsistent than what we thought before in terms of properties. This is, optimistically speaking, exciting, as this discrepancy has scope to detect new, more mysterious, more enigmatic findings. But still, as of now, these discoveries have truly been rattling to the whole physics community. and it continues to be explored, and the anticipation has never been higher. You see, this problem has appeared and reappeared. The numerical discoveries have only become increasingly drastic and stark. And this, ultimately, is the crisis in cosmology.